sure to record. Now we are recording for our second Zoom session on acoustics. I will share screen here and pull up from where we were last time. And you'll see the notes here, and we had kind of covered the first page. We talked about, molecular movement in air. We talked about sound waves, about how they are not really going up and down. Here's our second person. We got Sir Ramirez. All right, how are you doing?
Good, how are you?
Good, good. You haven't missed much. We just started here, and I was just kind of reviewing what we covered last week. And in our notes, we covered page 1, and we kind of got, down to about right here. We talked about 2 ways to represent sound. We talked about amplitude, frequency, and phase. And then we started to talk about frequency and period. Now I'm going to pull up the PowerPoint that we have here. Just a quick review of what we did last week. And you can see the tuning fork here. Making condensation, rarefaction. And what I really want to remind people of is this. 1 rarefaction and 1 condensation means 1 cycle. Okay, that's 1 wave. So 1 condensation and 1 rarefaction together make 1 sound wave cycle of 360 degrees. So basically moving down the line here, so 1 condensation, 1 rarefaction makes the up, 1 up and 1 down. So you're starting at 0 degrees, 90 degrees, 180, 270, and back to 360. Okay? And then we talked about, we draw sound waves like this because it's easier than drawing them like this, but sound really doesn't go up and down like that. Otherwise, we'd be doing this when we listen to each other. Okay? And then we gave another example out of a speaker. Here's a speaker making a low frequency sound, and this speaker making a higher frequency sound. And notice here, 1 rarefaction, 1 condensation, 1 rarefaction, 1 condensation is shown by a down, an up, a down, and up. So you've got like 2 cycles here, sort of. Here, the sound is more treble, higher pitched, and so you can see that the wavelength is shorter. What we mean by the wavelength is 1 cycle. 1 condensation, 1 rarefaction is smaller, shorter. And you can see that here too. 1 condensation, 1 rarefaction, condensation, rarefaction, they're tighter together. So there's 2 things to note here. The wave length, the physical length of the wave, that's called wavelength. And the second thing to notice here is the period. And the period, when you hear the word period, look at your wrist and pretend you're looking at a watch, because period involves the time it took to complete 1 cycle. So looking at this same thing here, pretend this is 1 second in length. Pretend this is time. So here we go. From here to here is 1 second in time. So the period, how long did it take to complete 1 cycle? If this is 1 second, it took a half a second to complete 1 cycle and a half a second to complete the 2nd cycle. So the period was a half a second. If this is time here, and this is from 0 to 1 second, how many cycles took place here? Well, 1, 2, 3, kind of 3.5. So 1 3.5 of a second. Okay, so physically the wavelength is shorter, and secondly, the time it took to complete 1 cycle was shorter. And that is what we mean when we describe the period. Okay, the period of sound. Frequency is the number of times something happens per some unit of time. Whenever you see the word frequency, just you could think of footsteps. How many footsteps per second are you taking? Okay, so in sound, how many wavelengths took place? How many cycles took place? How many condensation rarefactions took place in 1 second. And the number, that, or the abbreviation we use for that is Hertz, as in Hertz Rent-A-Car, H-E-R-T-Z, Hertz. 2 Hertz, 3 Hertz, 10 Hertz, 100 Hertz, it really hurts. But 100 Hertz means 100 cycles per second. 1,000 Hertz means 1,000 cycles per second. 10,000 Hertz, 10,000 cycles per second. And so if you can think of 10,000 Hertz, and I'll stop sharing here, if you think of 10,000 Hertz happening in 1 second, that means that the wavelengths are really short, like tremendously short, to have 1,000 of them take place in 1 second, compared to if one took place in 1 second, the period would be much longer. And so would the physical wavelength as well. So the length physically would be long, as well as the time it takes to complete 1 cycle. And as we said last week, elephants emit low frequency sounds, very low frequencies, below what we can hear. And those wavelengths are so long, they're probably about 100 feet long. A condensation is probably 50 feet, and a rarefaction is probably 50 feet. Those sound waves bend around objects. They go over rocks and trees, over the hill and down into the valley that's next. That's why foghorns on a boat use a low pitch, because low frequency sound waves are long and they bend around things, and whereas high frequencies, they're short, and highs don't bend. They bounce. They bounce. They're so high, they're so short, they don't bend around things. Bats use high frequency sounds to catch insects. They emit high-pitched sounds that bounce off the flies at night, and they can know where to eat them, because they're like radar. The sound waves bounce back, and the bat picks them up and uses the high-pitched sounds like radar. Hey, Roman, how you doing? Hey, big fella. There he is. There's not 3 of us here. There's 4 of us here, eh?
Yes. He won't leave me alone.
There you go. All right, so let's move into period here and talk about calculating it, because this will definitely be on quizzes and midterms and exams and everything, okay? Reading with me, frequency, number of times something happens, hertz. 1 hertz is 1 cycle per second. A sound with a frequency of 100 cycles per second is 100 hertz. And then we said here, period, the time it takes to complete 1 cycle. And so here's the trick to figuring out period. Period equals 1 over the frequency. Frequency is 1 over the period. For example, if a sound is 1 hertz, then its period is 1 second. And read with me here. If a sound is 100 hertz, then its period is 1/100th of a second. So period and frequency are inversely related. As frequency is increased, period is decreased. As period is increased, frequency is decreased. They are inversely. So here it is. Frequency is 1 over the period. Period is 1 over the frequency. Humans, we said, can hear from 20 hertz to 20,000 hertz. Okay? But let's just make sure we've got this. Let's take an example here. What would be the period of a 500 hertz tone? If a tone had 500 cycles per second, what's its period? So let's just try that. I'll stop sharing and have you look at me and tell me what it would be. Calculate it. You got a calculator there? What would be the period of a 500 hertz tone?
Isn't it 500?
Well, what is period? 1 over the frequency, right? Period is 1 divided by frequency. So go 1 divided by 500. And what do you get?
Hold on. My phone's acting up. So
Anybody got a calculator there?
0.002?
Correct. 0.002 seconds. 0.2002 seconds. You get that?
Mm-hmm.
So what if I asked you now, what is the frequency of a tone that has a period of 0.002 seconds. How would you figure that out? You do 1 over the period. So now to take 1 and divide it by 0.002. And what do you get?
500.
Correct. Okay? That's what you do. Let's try 1,000 hertz. What's the period of 1,000 hertz? What do you got? Tell me.
0.001.
Correct. 1/1000th of a second.
I've been muted
0.001.
this whole time.
Pardon me?
I was wondering why you couldn't hear me. I'm like, I'm saying it. I
Ah,
was muted.
okay. I don't know why I couldn't hear you. I heard something. I heard sort of a whisper, sort of a, but I wasn't sure what you said. So now on a quiz, if I asked you, what's the frequency of a sound that has a period of 0.001 seconds? What's the frequency? The period is 0.00. What's the frequency? Oh, we're frozen.
1,000.
Correct. 1 divided by 0.001 is 1,000. The relationship is inverse. Always remember, its period is 1 over frequency. Frequency is 1 over the period. Very good. Now let's move on in our notes to wavelength. Let's go down the page over here. You see wavelength versus frequency? So now we're not talking period so much. Now we're looking at the physical length, the length of the wave. Wavelength is also inversely related to frequency. Do you see the notes that I'm highlighting here? As frequency increases, the wavelength gets shorter. Recall, period is also inversely related to frequency. Hello, we got Renee here. We got somebody else? No, Ariana. Ariana. Good stuff. Welcome. Okay, so reading the notes here, just like period, wavelength is also inversely related to frequency. But there's something involved with wavelength. Let me stop sharing and look at you here. We said that period and frequency are inversely related. Period is 1 over frequency, frequency 1 over period. The physical length of a sound is also related to the speed of the sound. Now, the speed of sound in air, or the speed of sound in water, or how quickly sound travels through a railway track, steel, okay? Sound travels at different speeds in different mediums. Air is one thing. Air is a gas. Water is a fluid. A railroad track is metal. Sound goes fastest through metal, it goes slower in water, and it goes even slower in air. But that speed of sound it also fits into the wavelength. So now I will share screen and we'll look at the notes here again, and you'll see what I mean. Read with me what it says. Wavelength involves speed of sound. Look where I'm highlighting this. So this is another formula that we need to make sure we memorize, okay? Because this is also stuff that appears on quizzes, midterms, and final exams all the time. Read with me where it's gray here. Wavelength involves the speed of sound. Wavelength equals the speed of sound divided by the frequency. Frequency equals the speed of sound divided by the wavelength. Speed of sound equals frequency times wavelength. Okay, well, look at this. Think of, you know what you can do? Right beside wavelength over here, you can just kind of write something like this. 5 is equal to 10 over 2, right? 5 is like 10 divided by 2. In other words, you could just always put 5 over 1 is like 10 over 2. 5 over 1 is equal to 10 over 2. Okay, but you can also, so we'll just call this wavelength. Wavelength of 5, wavelength of 5 is equal to the speed of sound, 10 divided by the frequency, 2. Okay, wavelength of 5 is, so, and it really, now I'm going to give it to you in truth. We'll say the speed of sound in air is 340 meters per second. Now, you are Americans. I'm living in Canada. We are on metric here, but do you all know what a meter is?
Yeah.
It's about a yard, isn't it? It's 39 inches. It's a little bit longer than a yard. And a kilometer in Canada it's 1,000 meters. It's about a little over a half a mile. Okay? So you guys deal in miles, we deal in kilometers. For you in the United States, what's freezing? 32 degrees. In Canada, 0 is freezing. What's boiling in the United States? 212. In Canada, 100. Makes more sense, doesn't it? Freezing is 100, boiling is 100. So yeah, freezing is 0 and boiling is 100. We do everything in tens. Metric, everything is in 10. Now, the speed of sound is 340 meters per second. It's something like 340 yards per second. That's, if you calculated it all out, I'll put it to you in feet. It's 1,130 feet per second. That's the speed of sound in air, or 340 meters per second. Either way, I'm giving it to you in metric and I'm giving it to you in regular, okay? Now, how fast do you think that is in miles per hour? How many miles an hour does sound go? Well, I've calculated it. I used the 1,130 feet per second and figured it out. It's about 766 miles an hour. So you think of a jet. How fast do jets fly? They fly about 600 miles an hour. So they approach the speed of sound, but not quite. They don't quite get to the speed of sound. Only, you have to break the sound barrier. And that's 766 miles an hour. When you go faster than that, you're going faster than the speed of sound. Okay? I'll stop sharing and we'll look at our notes here for a second and I'll show you what I mean. But when you think of these things here, of these 3 little things right here that I'm graying out, they are all that work together. Wavelength is speed of sound over frequency, or frequency is speed of sound over wavelength, or speed of sound equals frequency times wavelength. Well, if we said wavelength is a 5, speed of sound, if 5 is equal to 10 divided by 2. Or you could say 2 is equal to 10 divided by 5. Or you could say 10 is equal to 2 times 5. You see what I'm saying? That's all I'm doing here. So, example for 100 hertz. Okay, the sound is exactly, I said 340 meters per second. It's truly 343, but I don't care. If you use 340, good enough for me. Close enough for government work, okay? So let's find out the wavelength. How long is a wave? How long is a particular wave? What wave are we interested in? 100 hertz. So here we go. For 100 hertz, I want to find out how long is the wavelength. How long is one condensation and one rarefaction of air molecules? How long is that for 100 hertz? A sound that takes 100 cycles per second. Wavelength is equal to speed of sound divided by frequency. Just what I'm showing right here. So you say wavelength is equal to 343 divided by 100. And when you do that, you get 3.43 meters. 3.43 yards about. How long is that? That's about 10 feet long, isn't it? 3 times, 3 feet. 3 times 3 is 9. Add a little bit more and you got about 10 feet. It's about 10 feet long. That's pretty long. 5 feet long is the condensation and 5 feet long is the rarefaction. One wavelength, one cycle. Let's look at, you can do the same thing in feet. Let's calculate it in terms of feet, not in meters. Let's look at it in feet. Look at this. Wavelength is equal to 1,130 feet per second divided by 100. And what do you get? 11.3 feet. There you go. Same thing, just different language. Okay? One's Polish, one's German. They're saying the same thing, they're just talking in different languages. One's metric and one's imperial, or what England and United States. You guys, England and the USA are the only countries in the world that don't use metric. I'm laughing. You know what? I'm part American. My mom was born in Michigan and my dad was born in Iowa. And I have a U.S. passport and social security number, so I'm dual. I have both citizenships. But my feet straddle both sides. I got my feet in Dixie and my head in the clear blue north. Anyway, no problemo. So what we've got here, you can calculate it in feet, you can calculate it in meters, doesn't matter, but the point is the formula remains the same, okay? Let's do a different example. Let's see, look at a different example here, 250 hertz. Take a tone that has 250 cycles per second instead of 100. Well, what's its wavelength? 340 meters per second, speed of sound, divided by 250 is 1.3 meters. Look at that. If you want to calculate it in feet, 1,130 feet per second divided by 250 is 4 feet. Done. Okay, look at 8,000 hertz. Now I'm highlighting a different one, 8,000. What's the wavelength of a sound that has 8,000 cycles per second? How long physically is its wavelength? 340 meters per second divided by 8,000 is 0.04 meters. That's small. Let's do it in feet. Okay, 1,130 feet per second divided by 8,000 is 0.14 feet. Just get a calculator, 1130 divided by 8,000, you'll end up with 0.14. Well, that's like a tenth of a foot. I mean, that's like an inch. It's pretty small, okay? So it just tells you, here's an important concept of all of this. Low frequencies bend around objects. Think of the elephants. High frequencies bounce off objects. Think of bats using high-pitched sounds like radar to bounce off the bugs so their ears can pick it up and they know where to find the fly to eat it. Okay? Lows have long wavelengths. They bounce around and bend around objects, I would say. Highs have short waves that bounce off objects. Think of bats. What does this have to do with hearing aids? Have you ever heard someone who's wearing a hearing aid? Have you ever heard the squeal of a hearing aid, the whistle? That's because high-pitched sounds are bouncing off the guy's eardrum and are bouncing out of the hearing aid. And they're getting picked up by the mic. It's like if I'm talking into a microphone and I go too close to the speaker. So now I'm going to get that feedback, because sound coming from the mic is going right into the speaker, and then it's going back into the mic. It's getting a loop feedback. The whistle in hearing aids is high-pitched, and it's caused by high-frequency, little short sound waves bouncing off the guy's eardrum, leaking out of the hearing aid and getting picked up by the mic, amplified again, bouncing off the eardrum, leaking out of the hearing aid, picked up by the mic, and you're getting that circle happening. Feedback. Okay? So all of this stuff you're learning in acoustics has clinical reality in your field. Let's move down the page. Let's go down to the next page here, and where we can talk
a little. Question before you move on.
Yes.
So the speed of sound, the 343 meters,
yep.
That's always going to be 343 meters.
That's constant, and that's the same for all frequencies.
Okay.
All frequencies travel the same speed in air.
I just wanted to make sure.
Yeah, and that's a good question. Glad you did.
Okay.
All frequencies travel the same speed in water, which is faster. All frequencies travel the same speed in steel. Okay? So never think that's the different frequencies travel at different rates, because that would be a real acid trip. I mean, really, we'd be going all over the place. That'd be nuts. Okay, so always remember, frequency means different wavelengths. Frequencies mean different periods, different times that it takes to complete one cycle, but the speed of sound in air is constant for all frequencies. Always good to ask questions. Glad you did. Let's look at our notes here now. Speed of sound. Let's just talk about it. This is kind of interesting. This isn't stuff you have to really memorize. I'll tell you when you do. Okay? At room temperature, at room temperature, speed of sound is about 340 meters per second, or about 1,238 kilometers an hour, or about 766 miles an hour. You see where I'm highlighting the page here? Okay? Look at the speed of light. Look at the speed of light compared to the speed of sound. The speed of light is 100 million times faster than sound. Oh my God. 100 million. Like, hear the sound of fast. Light goes way faster than sound, and light travels through outer space. Light doesn't need air or fluid or steel to travel through. Sound does, because sound involves squeezing and separating of molecules. But there are no molecules in outer space. There's no air. Okay? But yet light goes through it. Light is a totally different thing. Light travels 100 million times faster. And we all know this and we've all experienced this. When you see someone across the street or down the block and he's hammering something and it goes, it takes a while for the sound to get to you. Okay? And that little while is 766 miles an hour. So even when you yell across a canyon, hello, 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 that's the sound bouncing back. Light is insane. Light goes, let's read notes here. Light, look at the speed of it. Light travels, look at this where it's grayed out. Light travels about 300 million kilometers per second, or about 186,000 miles per second. Per second. What's the proximity of the... Uh-oh. Are we freezing? Yep, I think so. Here we go. What about the moon? How long does it take light to get from the moon to us? 3 seconds. That's at 186,000 miles per second. It takes about 3 seconds. You don't have to know this. I'm just talking. How long does it take light to get from the sun to us? About 8 minutes. How long does it take light to get to us from the nearest star? 4 years. You're traveling 186,000 miles per second, and it still takes 4 years for light to get to us from the nearest star. That shows you how far away it is, how big outer space really is. Sound is a totally different animal. Sound, 766 miles an hour. Just want to bring that home. I think it's just important that we just kind of get a context here. This is what I need you to know right here. Speed of sound is 4 times faster in water than it is in air. And put a star by this one too. It's 14 times faster in metal. 14 times faster in metal. So speed of sound is 340 meters per second. Multiply that by 4 and you'll get the speed of sound in water. Multiply 340 by 14 and you'll get the speed of sound in steel. Remember what we said last week? That's where First Nations people would put their ear to the ground to listen for the buffalo coming. They're trying to hear the hoofbeats of the buffalo because the sound goes faster through the ground because it's hard, it's an object, faster than it does through the air. So there, and same with people listening to a railroad track to listen for the train coming. You'll hear it quicker coming through if you put your ear on the railroad track than if you listened through the air. Okay? That's where the saying is, I'll keep my ear to the ground. You're looking for a job? Well, I'll keep my ear to the ground for you. If I hear anything, I'll let you know. Okay? Sound goes faster through steel than it does through water, and it goes faster through water than it does through air. Now, this is kind of here's what I need you to look at carefully too. This is one little section here. Speed of sound is influenced by two things: the density and the elasticity. Those two words, density and elasticity. Density is the mass, that, you know, how tightly the molecules are together. Like steel is way more dense than air. Okay? I mean, if you look at me once here, I can move my hand through the air, so air isn't very dense. Okay? But here's my hand. I can't. Okay, this is much more dense than the air. Okay? If I take a bat and hit my head, it's going to hurt because the bat is way more dense than, well, then again, my head's pretty dense too, but you know what I mean. Okay? So the density is how closely packed the molecules are together. You can think of the density as the mass of something. And when you think of the word elasticity, you think about how stiff the object is. Is it stiff? Or is it, or is it tight? Okay? Two things influence the speed of sound: the density and that stiffness of it. So now we take a look at steel and air and water again. Here we go. Sound is influenced by the density and the stiffness of it. What does it say here? Inversely, yeah, right. You forget about this one. Inversely related to the square root of density, directly related to the square root of the last. Forget that. That's stupid. Here we go. This is what we need to look at. The more dense an object is, the slower sound travels through it. So you would say to me, that doesn't make much sense, Ted. You just said sound goes faster through steel than it does through air. And steel is a lot more dense than air. And I would say, yes, you are right. That's true. Then why does increased density, slow the speed of sound? Well, here's the other side of the equation. Think of stiffness. The stiffer an object is, the faster sound goes through it. And steel is also a lot more stiff than air is. Much more stiff. So here's the rub. But fluids and metals are more dense than air, so why does sound go faster through those media? Especially if you said the more dense something is, the slower the sound goes. Well, steel is 6,000 times more dense than air, but steel is also much more stiff. Elasticity. It's much more stiff than air. Think of elasticity as the ability to resist being bent or deformed. Think of it as stiff. And the elasticity of steel is 1,230,000 times more than the stiffness of air. So I think what I'm going to just put here, just so we keep it, stiffness. More elastic, and I'm just going to write in the word stiff than air. Much more. Okay, elasticity has ability to resist being deformed. Elasticity of steel, or the stiffness, and I'll put it again here, of steel, okay? So much, and I gotta shrink this thing here, much greater than. Okay, so there you have it. So steel is way more stiff than air. Think of elasticity or stiffness as ability to resist being deformed. The elasticity or the stiffness of air is way more than the stiffness of steel, is way more than that of air. So the bottom line is the greater elasticity of steel far outweighs its greater density. That is why sound goes faster through steel than it does through air. Even though steel is more dense than air, it's also way more stiff than air. And its stiffness outweighs its greater density. Its greater stiffness outweighs its greater density. And that is why sound travels faster through air, through steel. So here we go. Recall, wavelength, frequency, and speed of sound are all interrelated. In water, the same frequency travels faster than it does in air. Its wavelength is going to be longer too, but don't worry about that. Who cares? And here's the question that Nicole asked. Speed of sound has no relation to the frequency. A 2,000 hertz tone in air travels exactly the same speed as a 1,000 hertz tone. Now we get out of the tough stuff. Let's get to the easy stuff. More fun stuff here. And then we'll be done this section. We will be finished Unit 1. Let's talk about the Doppler effect. The Doppler effect first. We've all heard cars coming to and fro from us. Here we go. I'll show my. We've all heard cars coming to us and going past us. Like this. An ambulance. How come cars go higher pitch, higher? It gets lower. That's because the speed of sound in air, 343 meters per second, that is added to the speed of the car itself. So if the car is traveling, 100 miles an hour toward us, that is also added to the speed of sound. So guess what? The wavelengths get shorter because it gets squeezed. All the wavelengths from the car of its sound are squeezed because the car is moving toward us at 100 miles an hour. We're standing still, but the car is moving to us. So the waves literally get squeezed. And when they get squeezed, they get shorter. And when the wavelengths get shorter, the frequency goes up. And the exact opposite happens when the car passes us. When the car passes us, the sound is 340 meters per second minus the speed of the car. And so the wavelengths get larger, they get longer, and so the frequency goes down. Indianapolis. Okay, Doppler effect, or a siren of an ambulance or a police car. You'll hear it get higher pitched as it reaches toward you, and as soon as it passes you, it gets lower in pitch. That's called the Doppler effect. Okay? Don't you need to memorize it, just kind of know what it is. And read your notes and it will explain to you what that is. Another phenomenon of sound, of the speed of sound, is breaking the sound barrier. And you've all heard of breaking the sound barrier. Breaking the sound barrier means you've gone faster than the speed of sound. So let's look at this in a PowerPoint here and kind of move all the way down. Here's a picture breaking the sound barrier. Now here's a jet, and it's broken the sound barrier. It's going faster than 766 miles an hour. What happens there? Well, the jet is increasing in speed, going faster and faster, and the sound only goes 340 meters per second. So it's squeezing those waves because it's catching up to the speed of sound. And now the waves are getting squeezed all together. And once it pushes through that sound barrier, you've got this big vacuum of molecules, this big rarefacted empty area just behind the jet. And then all those squeezed molecules in front of the jet, wham, fill that empty space. And that's sonic boom. So the jet is speeding toward is approaching the speed of sound. So the wavelengths are getting smaller and smaller and smaller, and they're all squished together. All the molecules are squished together. And suddenly when the jet pushes through and gets faster than the speed of sound, all those squeezed molecules fill in this empty vacuum behind it. And that's the boom. You want to hear another example that we're more familiar with? We've all hung around in a locker room at the gym, and just to tease your friend, you take a towel and you do this with it. And then you snap somebody in the ass with the end of your towel. Hurts, don't it? You know why it hurts? Because that of the towel has broken the sound barrier. That's a tiny little sonic boom. The crack of a whip. You met that? That's the sound. It's breaking this. That's the sonic boom caused by the very end of the whip cracking, breaking the sound barrier. The very end of your towel when you snap it at somebody's ass, that is actually moving faster than 766 miles an hour. No wonder it hurts. Hurts like hell. Okay, so that's just something to kind of keep in your mind. That's just a more familiar, smaller example of a sonic boom in our lives. That's why you come to OTC, to learn about how to how to snap towels at people. Great, nice guy. Okay, I'm gonna go now. Let's see, I'll stop sharing this. I think what I want to do is finish our notes here with our last piece. I don't want that. What I want is I want to share screen, and I don't want that ridiculous thing. Hit. I don't know why this is frozen up. Like, hang on, you guys. Okay. Escape. I think I'm going to just close that. There you go. Boy, I had to shut down the PowerPoint to get it to stop. I should have snapped it with the end of a towel. Okay, here we go. We finished with this last thing. I think it is anyway. Oh no, I lied. Okay, just about. Whoops. Hang on. Okay, there's something to look at here called a sound field. Now, a field, it has nothing to do with a football field. A sound field is just a room in which sound is taking place. That's all it is. Sound is always taking place in some area. I mean, it's not taking place always 1,000 miles up above or 1,000 feet above the earth. When we're talking in rooms, or we're talking outside, or we're talking on a football field, or we're talking in a church, okay, in an auditorium. That's a sound field, a place where sound takes place. A free field means no walls, nothing for sound to bounce off. That's very rare, hardly even exists in reality. Okay? A sound in a space where there's no reverberation or echoes. No reverberation or echoes. A free field, very rare. Reflection occurs when sound travels from one medium to another. Here you go. Read this with me. Sound energy taking place in air increases because of added reflected sound off the wall or a second medium. Just like a mirror increases light from a lamp. The light is traveling through air and it bounces off the mirror, and now you've got more light. An actor enclosed in a theater sounds louder than in an open space. Like if I'm talking to you in a telephone booth, I'm going to sound a lot louder to you than if I'm talking to you in an open football field. And the reason why is because in a telephone booth, my sound is bouncing off the glass. And so you're getting added sound. Whereas in an open football field, there's not much for the sound to bounce off. So there's two things you need to memorize here. An echo is when the reflected sound occurs less, or it takes more than 1/10 of a second. Look what it says here. Echo is when the time delay between original and reflected sound is more than 1/10 of a second, more than 0.1 second. Think of the Grand Canyon. Hello, hello, hello. That's more than 1/10 of a second for the sound to bounce back. It's like a half a second or a second. That's an echo. But if I'm in a gymnasium and I'm bouncing a basketball, you've all heard a basketball bouncing, when you're in a gymnasium. And it's not really an echo because the reflected sound is less than 1/10 of a second after. It's like, bah, 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 bah. That's reverberation. So when I'm bouncing a basketball in a gymnasium, what you're hearing, that extra echo or whatever, it's not truly an echo. That's called a reverberation. And why? Because the reflected sound is less than 1/10 of a second after the original. Grand Canyon, hello, hello, hello. Those reflections are more than 1/10 of a second. But being in a gymnasium or acting like Elvis Presley, be-bop-a-loo-yah, be my baby. You get that in a gymnasium, that's reverberation. Why? Because the reflected sound is less than 1/10 of a second after the original. Something to memorize for a quiz. Just preparing you just so you got it, okay? So we can move now down to our final area here. I'll just kind of go like so. Put this here, move on down. You've got something called a standing wave. And a standing wave doesn't mean a wave that stands up, okay? A standing wave is when the reflected sound cancels out the original sound. Now, to understand that, I would have to, of course, have closed my PowerPoint. What a loser. I should have left that open because I want to just show you. It's best to show you here, just in terms of a picture, okay? We'll pull up this puppy again and hope that it behaves. Yeah, it's almost at 10% up. Come on, computer, speed up. Okay, here we go. What do we mean by a standing wave? Look at this. Look at the bottom. When the original sound is canceled out by the reflected sound. Remember the slide from last week? We said that sound takes place over 3 dimensions. These are different in amplitude. These are different in frequency. These are different in phase. Look at this. Same amount of waves as this one. Very same amount. It's just that these are taller. So these two tones are different amplitude. The middle panel, same amplitude, same height of the wave, because the height of the wave represents amplitude, but this one has fewer cycles than this one does. If this is 1 second and this is 1 second, there's more cycles in the bottom one here than there are in the top. So these two are the same in amplitude, they're just different in frequency. Whereas the top pair are the same in frequency, they're just different in amplitude. The bottom ones, they're the same frequency, they're the same in height, same amplitude. How are they different? In phase. So if you added this one up to this one up, you'd have the sound of one hand clapping. Ah, so. Okay? You'd have silence because they would cancel each other out. A standing wave in an auditorium is when the reflected sound is completely out of phase with the original sound. And then you've got a dead spot in the room. That's why you have acoustical engineers. You don't just build auditoriums like just to build them. They are designs with acoustics in mind so that you can get rid of standing waves. Okay? Anechoic, circle this one. Anechoic room is a soundproof room. Soundproof. It means no sound can get in. It's totally dead quiet. It's a free field. You know why? Because all sound is absorbed by the walls. You can yell all you want, no one's going to hear you on the outside. And people outside can yell all they want, no one's going to hear you on the inside. It's soundproof. It means without echoes, anechoic. It's meant to imitate a free field, but it's really quite soundproof. It's very expensive. When we test hearing in this field, we don't use soundproof rooms. Just like a watch can be waterproof or it can be water resistant, right? Waterproof means you can dump the watch into a sink of water and nothing will happen. That's waterproof. Most watches aren't waterproof, they're water resistant. so that when you're washing the dishes, a drop or two of water on the watch isn't going to do anything. It's okay. It's water resistant. Well, that's the same with sound rooms. When we test hearing, we use sound resistant rooms, rooms that block out lots of the sound, but not all of it. An anechoic room is completely soundproof, and they cost millions of dollars. Okay? Sound treated rooms are what we use in our field. They got really thick drywall, and for most part, they're pretty good at blocking out background noise, but they're not 100% soundproof. Okay, just so you know that. The last thing, here's the stuff. Oh boy, there's always more, isn't there? You know what I think I'm going to do? I'm going to probably I'll probably just kind of cover this stuff here, and then we'll stop. And then we'll continue next week and finish off this stuff, just so that we really understand. In fact, I think what we'll do next week was we'll just review everything we covered in these first 2 weeks, and we'll get to the very end of this section, which is down here. That's the end. Okay? But I'm going to I think it's all too much to finish that. Let's just talk about one last thing, because we got about 7 minutes left. We're good. Resonance. What the Sam Hill is resonance? You know, when I'll stop sharing here for a second. Think of a wine glass at Christmas. All I got in here is coffee, but you got a wine glass, you lick your finger. You know how you can make it vibrate? You know how when you can take a pop bottle and blow over the top of it, and all of a sudden you can make it resonate? Resonance is the favorite vibrating frequency of an object. It's what it resonates with. Resonance is determined by an object's mass and stiffness, by an object's density and elasticity. Remember those two terms we heard earlier, density and elasticity? Density is mass, elasticity is stiffness. And just like they affect the speed of sound, they also affect the resonance. Now I'm going to give you an example. You're sitting in your couch, watching TV, quietly doing your own thing, and the neighbors upstairs are playing loud music. What comes through your ceiling? The bass guitar and the drums. Boom, 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 boom. The low pitches, why? Because your ceiling is dominated by mass, and mass resonates with low pitches. All right? Stiffness resonates with high pitches. I'll give you an example. Think of a locomotive, a big train locomotive, the big engine that's at the front of the train. Do you think it's mostly mass or stiffness? It's mass, baby. That puppy's heavy. Can you jiggle a locomotive? No. You're going to be 100 people pushing it this way, and then 100 people pulling it the other way, and then 100 people. You can't jiggle a locomotive. Why? Because it's massive. It only wants to move or vibrate with low frequencies. Think now of a spring, a thick spring, kind of about, as thick as my finger, a big spring sticking out of the wall. And I'm going to grab that spring. If I push slowly on it and pull slowly on it, it's going to be really hard. But if I stand there and go, it's easy. Why? Because the spring is stiff. Stiffness vibrates with high frequencies. Mass vibrates with low frequencies. This is important. Again, you can't jiggle a locomotive. It's got a lot of mass. Mass vibrates or moves back and forth, low frequencies. Fewer times per second. Slow, doesn't like to move to be changed. It's massive. Stiffness resonates with high frequencies. And high frequencies resonate stiffness. So think of a stiff spring sticking out of the wall. For me to move it back and forth slowly is hard, but Yeah. Easy peasy, Japanesey. What does this have to do with the price of tea in China? Everything. Check this out, and then we will check ourselves out and see you next week. Here goes. Look at your outer ear. See the weird shape? Weird shape, funny little bowl here, and then your ear canal, about 1 inch long in United States, about 2.5 centimeters in Canada, okay? About 1 inch long, just like the wine glass at Christmas. Guess what? This shape resonates with high frequencies. It's dominated mostly, and guess what frequencies it resonates most with? Speech. The high frequencies of speech. Now think of speech just for a second here. You've all heard of vowels and consonants. Put your hand to your throat. Put your hand to your throat and say, mm. Now go, ah. Say, ooh, ee. You can feel it vibrate, eh? Can you feel that? Now, keep your hand to your throat and say the letter S. S. Say F. Can't feel it, can you? Say TH. Can't feel it. Those are high-pitched speech sounds. The ones you make with your lips. Okay? Think of the words hat, fat, gat, hat, fat, bat, sat, mat. They all have ah, ah, ah. Well, guess what? Ah is a low-pitched sound in speech. What are the high-pitched sounds? So hat, fat, cat, sat, they all differ because of the consonants. The vowels are cheap. We have 5 vowels in English and thousands of words, and every word has a vowel. So vowels don't tell you crap about what the word is. Consonants. Church, perch, lurch, search. Pin, tin, fin, kin. Kittens, mittens. Okay? Hard of hearing people lose treble hearing. They lose high frequency hearing. When you can't hear high frequencies, you lose the ability to tell what was the word. Not that words are spoken, but what did they say? Oh, kids, you young kids mumble today. Young kids mumble. That's what elderly people say. Why? Because they've lost treble hearing. They've got trouble hearing treble. You know what it's called? Presbycusis. Sounds like Presbyterian. Presbyterian means Church of the Elders, as opposed to the deacons. Presby is the Greek word for old. Presbyopia, your arms aren't long enough to see the page. You can't see close up. Hit you when you're 40. Presbycusis is treble hearing loss. Hit you when you're 65. That's what you're going to be fitting, is people with presbycusis. Their outer ear might resonate with those high pitches because that's the way either God made it or we evolved, but the ear is made for speech. If we didn't speak, our ears wouldn't look like this. We'd have dog or cat's ears, okay? But our ears have that shape to naturally resonate with high-frequency consonants, but when you get hearing loss, it's not enough, okay? So now you need hearing aids, and guess what? Most hearing aids amplify treble. Here's how elderly people hear. I'm going to show you something just for fun. I'll get a piece of paper here. Give you an example. I'm going to roll up a piece of paper like a horn. I'm going to make a picture. Here we go. See this horn? Okay, I'm going to talk backwards into the horn. What I'm doing is cutting off the high frequencies of speech. The high pitches of speech, you can't hear them quite as easily. Sound is more muffled. But if I speak into the opposite end of the horn, you can hear my high frequencies much more easily. And that's exactly what hearing aids are trying to do. Amplify treble. Because elderly have trouble hearing treble. The thing about consonants is they're softer. They're naturally softer. So if you say the word speech, 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 the loudest part of that word speech is E. E. It's pretty soft. If I say the word church, church, If I raise my voice, church, go to church, you heathen. Okay. If I say church, it's the loudest part of the word church is it's the throat. Those are vowels. Those are louder and lower. But consonants, the ch of church, those are high-pitched and they're naturally softer. And that's why you've got this outer ear to help, because the outer ear resonates with the high pitches of speech. But when you've got hearing loss, of course, it adds to that. So this isn't enough to naturally amplify those high-pitched consonants. But that's where we're going in this course. In a few weeks, or 2 weeks from now, we'll start studying the decibel, loudness. Instead of wavelength and frequency, we're going to look at that other dimension of sound, the intensity, the amplitude. Then we'll put it all together and we'll talk about complex sounds like noises, traffic, music, speech. Okay, the most important one is speech. And we'll cross this discussion again here. And then that's the whole first half of acoustics. After that, you get a midterm, and then we talk about psychoacoustics, perception of sound. But it's a neat field. I think you guys are going to like it. Anyway, I will say ciao for now. Live long and prosper and all that stuff. See you when I look at you. Basically, does anybody have any question?
I sure
I have a question.
Yes.
You can go first.
Shoot.
So for the quiz this week, let's do this weekend. Is that
Yeah.
going to cover stuff that you said in these two?
That's an excellent question. Let me pull up the quiz right now, and I'm going to make an executive decision. How about that? Okay? I'm glad you're asking that question, actually. I'm really glad you are. Let's see. Oh, 110, quizzes and tests. Ooh, let's look at this one here. Ooh, let's look at quiz 1 for acoustics. Let's check that out. Check it out. What do we got on here? On a sound wave, look at this. The up portion represents condensation or rarefaction, circle 1. What's the period of a 250 hertz tone? Da, 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 da. Speed of sound in air, wavelength is calculated, da, da, da. Spectrum shows speed of sound for an echo. I'm just quickly reading this. You know what? This quiz, yep, you should be able to do this quiz. Yep, because all the questions on it deal with the stuff we've covered up till today. So we're good. Quiz 1, leave it exactly as it is. Yep. So whatever the due date was for that quiz, when did she say the due date was, Ms. Royer? She said, when was it due, the 10th?
Sunday, I think.
Yeah, go for it. Yep. You'll be able to do it on the basis of what we covered today and from our Zoom session last week. Everything on that quiz is doable. All right?
Okay.
Okay, you guys. It's been a slice.
Nicole has a question too.
Nicole, yes.
Yeah.
Oh, always Nicole. It's always, she's always got something. You always go ahead. I'm just teasing you.
No, I was just wondering if there was like audio versions of these books somewhere, like online or at a library.
Audio version of the books?
Mm-hmm.
Nope.
Or some.
No, this is about as audio as it gets.
Some of these words are like.
Yeah. We've got the Zoom sessions. Actually, if people are really taking notes and following these Zoom sessions, this is like 95% of your course material for the quizzes, midterms, and final. It's all in these sessions.
Okay.
This is almost like a cheat sheet of your books. I'm taking your readings and actually condensing them right down into these notes that you're using and these particular Zoom sessions. And actually, the person who's going to be doing the test, who's going to be giving us the test, is Roman. He's going to be grading the tests as well. So you got to watch out. That he's a stickler for detail.
Yeah, I've got 2 today. I've got my.
Oh, you got 2 today. Great. 2 is more better than 1, right? There you go. Double the trouble. All right, you conniving connivance.
There she goes.
There you go. We'll see you when we look at you. Ciao for now.